So we spent some time looking at pumps and how we develop fluid power, how to size the pumps and so forth. Now let's look at the rest of the components, the fundamental components of a fluid power system, working up to the point where we can actually put a system together and make it do something. So the next thing, you've got your pump that's developing the power. The power is going out through some lines of some kind, and then usually the next thing it hits is a valve. And the valves will do a number of different things. They're gonna control how much flow or the nature of the flow that's coming out of there. So they're gonna control the pressure. So we're gonna see some that are relief valves and so forth that are gonna protect the system, so keep the pressure from going above a certain point. We're gonna see some valves that control how much flow goes out there. And we talked about that in our examples, the fact that we can limit flow rate. If we have so much available, we can put a flow control valve in there and say, hey, we don't want all that flow to go out there. So we can limit pressure, we can limit flow, and then we can control where it goes. So we can send it down different paths to actuate different things or affect different things. And so we're going to look at pressure, volume, and control valves, all three of those. So let's start with the pressure control valves. That's what we're going to look at now. And we're going to go with the simplest one that is in almost every system, and it's a relief valve. And so as I move to the slide here, take a close look at these relief valves. You see in the center of the slide there the JIC symbol, and they're pretty descriptive. Like I said, these JIC symbols are pretty descriptive of what goes on. So we got a block here, so you see the line. This is where the line is coming down. It actually shows the fluid going into a reservoir here. So the fluid comes down, and the path of the fluid is blocked. So when you see a block like this in a valve, and we'll see a lot more of these, this block can slide back and forth. So you can kind of picture imagining the block sliding to the left. If it slides to the left far enough, that's going to line up this arrow and the flow path with the path of the line, and it's going to allow fluid to flow through it. Okay? And so what forces that block over is this pressure sensing line up here. And we talked about these with the pump. So this is just a line that senses pressure. It's a very small port, usually within a valve. And it could even be more simple than that. When we look at the valve over here, we'll see it's just really, really basic. But in function, it says, okay, we're going to sense the pressure upstream. When that pressure gets high enough, we're going to allow this block to work against the spring over here, push that block over and allow flow to go through. So when the pressure gets high, we open up and allow flow to go through. So it's like a relief valve or a safety. So, we put this after a pump typically to protect the pump. Over here is a very simple type of pressure control valve or relief valve. And it's a cutaway, so these blocks you see up here are actually a spring. So this is a spring up in here that's pushing down on a ball. This is a ball that's seated on here. So the flow path would be from the bottom on this particular valve. And the pressure here is going to act against this bottom of this ball. And we have pressure over a certain area, and that's going to develop a force. And when that force gets high enough, it's going to move that spring, push the spring up. That allows the flow to come up through here and go out through the outlet of the port. So it's pretty simple. You just open the spring. When the pressure gets high enough, it moves the spring and opens it up. Okay, now one of the things that we realize with this, with springs, and the spring equation, that the force equals K times X, the spring constant times how far it moves. And so what that tells me is, hey, as my force gets bigger, my valve is going to open up more and more. Okay, so I'm going to get a progressive opening. And so what we do is we look at the flow through the valve, and this curve down here, the inside curve, is the flow rate that would happen through this valve as the system pressure gets higher. So as the pressure starts up, pressure goes up and up and up, nothing happens until it gets to the point where the pressure here, the force developed by that pressure over the area of that ball is big enough to counteract the spring force that's pushing down on the back of that valve. That begins to open it up. We call that the cracking pressure. That's where it cracks open right there. And then if we start to get flow through the valve, so you can see the flow through the valve goes up. So more and more flow, and as the flow gets bigger, and this is pretty linear because this is a linear equation, F equals Kx. And so the higher the pressure, the more the flow goes down there, all right? So this is what we call a direct acting relief valve. Very, very simple. Just push the spring and push it open. Okay, now we got to follow this thing over on the right because this is what we call a pilot operated relief valve. And I want to spend some time explaining what a pilot operated valve is, because this is somewhat undesirable performance here. And we'll talk about that in a minute when we look at system performance. We'll see that this provides some undesirable performance in our system and reduces the amount of power that we can actually get out of the system, okay? Because we have to protect the system. We can't let the pressure get too high. But when it cracks very low and we get a lot of leakage over there, that's inefficiency, that's lost flow. So I'd really like this thing to stay closed and stay closed like a brick wall until I get to my maximum system pressure over here and open up. That's what I'd really like to happen. Okay, now, that's theory, that's ideal, we can never achieve that, but there are ways that we can get closer. And the pilot operated relief valve gets closer. That's what this other curve is on the graph, is the pilot operated relief valve. Now, what does it do? Well, it's this valve up here, and it's a little more complicated. You see, we still have this this poppet, we call it, or the valve that closes this off. So basically we have flow, and this valve actually shows flow going through this valve, so we could actually pretend that this outlet over here is closed. So we could just have the pressure sitting against the bottom of this relief valve. When it opens up, this is where the discharge would go. So this is where the flow would go through that. So let's just for the minute just ignore this outlet, assume that there's no flow going through the valve over here, but all the flow is just coming in and stopping. So basically we have pressure in here operating on that. So let's think through this. And again, this is kind of hard to get your head wrapped around, but let's think about it. So we have pressure here that's pushing up on this poppet, trying to open this valve to get down there. Well, what do we have counteracting that? We have a spring up on top that's pushing that closed, okay? But now we also have something else going on here. So we have a hole through this poppet, and that's on purpose. So it's a hole that allows this little wee bit of this flow to get up in here, okay? And now the flow could go on up, and there's another direct acting. This is just a real small direct acting relief valve up here. But it's a real small port, real low flow, much smaller than what the main flow rate is up in here. But this would be closed when we're below the system pressure. So if we think about a force balance now, and let me go back to my pen, and we'll put some forces on here. Let me do red so it stands out. So we're going to have, what do we have acting up on a thing? We have the pressure acting up on the bottom of that thing. Okay, so the pressure is pushing up from the bottom. We also have the pressure pushing down from the top. Okay, so if there's an opening here, and there's no flow, so the flow can't go through there, so we have an opening with no flow rate through that opening, through that orifice. That means the pressure on both sides is the same. So we have the pressure on the top side pushing down, the pressure on the bottom side pushing up. They counteract each other. Okay, now in addition on the top, so they would balance it, but in addition on top we have this spring. So we also have this force of the spring pushing down on that popping and keeping it closed. Okay, so there's like an extra force up here. This thing isn't going to open. Now, at some point as this pressure increases, the pressure gets higher and higher and higher here. If I look clear up on top, at some point it's going to open this little relief valve here. Okay, again, this is a really small one, direct acting relief valve, just like the big one over here that we just looked at a minute ago. It's going to push this open, and there's going to be some flow start to go through this, and it goes out what we call a drain. So we actually have a little line here that we have to port back to the tank at some point. But we got a little bit of flow sneaking out through there. Oh, so what's that do? If I got flow sneaking out through there, now I've got flow going through this orifice here. Ooh, okay, so flow going through this little hole. That means I'm going to have a pressure drop across that hole. So what that does is the pressure on the top side, this pressure that's pushing down on the poppet, this pressure starts to decrease. All right, so it starts to decrease. So as that pressure decreases, now this force gets a little bit smaller and smaller and smaller. But remember, I still have this spring pushing down here, so I still have more force on the top keeping the thing closed. At some point, when this pressure gets high enough and a little bit of leakage going out here, it keeps opening this up a little bit more flow rate coming out of that drain on the top. Eventually, this pressure gets down to where the sum of this pressure of the down force and the spring get really close to or get balanced with the pressure that's pushing up from the bottom. All right. When it passes that point, this thing is going to open. And when it opens, it goes all the way open. So the pressure, the spring force is not enough to hold it. The pressures are imbalanced, and it's not like this force is going to get a whole lot bigger. This is a relatively small spring that's holding the poppet down there. So that poppet is going to pop open and open up wide open. And so there's where I get this closer to a brick wall performance down here. So that thing really turns hard and I get really close out there. All right, so that's a pilot operated relief valve. So when it's open, it just opens all the way. It doesn't open a little bit and start to crack and leak. It opens really, really fast. All right, so what does that mean for us? Let's look at some system performance, and here's where it really comes into play. And I alluded to this when we were doing the examples in an earlier module. And the fact that here's a system. So this is a very simple hydraulic system, and even some of the stuff in the complicated systems and agricultural tractors and other equipment, this is really the fundamental of what there is. There's a pump in there that's creating flow, and that flow is available to whatever I'm putting downstream. So this could be cylinders and motors, and I don't care what else is going on down here, but this is my outlet, if you will, whatever I'm driving my equipment downstream here. So the flow is coming down out of here, but I've got this relief valve in there that's protecting the system. And so the idea is, hey, if this system pressure gets too high, this sensing line here says, oh, open the relief valve, let's allow that flow to come back to the reservoir. So this pump here it's cranking out flow, it's pushing stuff. If it doesn't have enough place to go downstream and the pressure gets too high, we allow some of it to sneak straight back into the reservoir down here, and that keeps my system pressure from getting too high and protects me. Okay, so what does that ultimately mean for me? So if I look at performance, and I showed you this graph before, this is one you're going to collect in the lab. You're going to look at a tractor, you're going to collect this performance to see what you're going to get. This is the curve. The curve is going to look something like this. Again, we think we should get ideal performance. Says that, hey, we got flow rate, we're going to keep at that maximum flow rate until we get to our system maximum pressure, and then we're going to say, oh, that's it. So we're not going to allow the flow rate to go any higher, we're not going to allow the pressure to go any higher. So we'd like to have this square box performance. We can't get that. All right, so what's going to happen? In actuality, what's going to happen is, as our pressure goes up, and we talked about this with pumps, more and more back pressure on that pump means more and more leakage. Okay, so that's just leakage. So the actual performance is going to drop down a little bit. My flow rate's going to go down as my pressure increases just because there's leakage back through the pump. Now at some point, this really starts to turn faster. And it turns faster because this is the point here. This is the cracking pressure of the relief valve. So this is where this relief valve in the system over here starts to open to protect the system and allow flow to go out. So now, as the flow goes, I advance the slide there. So let me come back. So as the relief valve opens and the pressure gets higher, I get more and more opening on that relief valve, more and more opening until the system will look something like that, till my pressure gets up to the maximum, and all the flow then that's coming out of the pump is going through the relief valve. None of it, so the flow rate is going to zero. So that means the flow rate out of the system. So this is the flow rate at the output of the system. The flow rate at the output of the system goes to zero. In this case, the flow rate out of the pump is not zero. The flow rate out of the pump is being directed or short-circuited through the relief valve straight back to the tank. Okay, so that's what my performance looks like. And again, if I look at the power is pressure times flow. So my power at this point at high flow and no pressure is zero. The power at high pressure and low flow is also zero. My maximum power point is somewhere in the middle here where I have a lot of flow and a lot of pressure. So that's the amount of maximum power that I can get out of it. Okay? Here's where the difference in relief valve comes into play. So if I have that cheap relief valve, the direct acting relief valve with the spring, I'm going to have performance that really curls off like that. If I have that pilot operated relief valve, I'm going to be able to hold this out a little bit further. My cracking pressure is going to be bigger. It's going to be able to hold it. I'm still going to lose flow because of the leakage, so that curve is still going down, but my cracking pressure doesn't happen till out here. Now I get a much sharper curve, a much sharper turn, and it looks something like that. Where's my maximum power point now? It moves my maximum power point way out here. All right, so all of the area between these curves is power that I have gained just because I got a better relief valve, one that's going to give me a little bit better performance and push that curve out. So this is, again, in the lab, we're going to collect these curves. We're going to look at these curves for a tractor and for some test benches down there. So we have a couple of different pieces of equipment that we'll look at, and we're going to try to measure this. So can we identify where that cracking pressure is? Can we have an idea of what kind of relief valve is in there? You know, how close does this get? What is the maximum power we can get out of it? And how does that compare to maximum flow, maximum pressure kinds of conditions? So this is the lab exercise that we're going to do. Again, it goes back to looking at these the pressure control valve, specifically the relief valve, and how good they are, the different kinds, whether it's a direct acting or whether it's a pilot operated. So that changes the shape of that curve completely. And again, we need to remember as we're designing systems, especially if we're designing something to run off of a power supply. We've got a pump and we know what our maximum pressure is, but where we can operate is we can't operate out at the outside of that envelope. We have to operate inside somewhere. So we have to understand that curve is inside of that dotted line, that brick wall thing, and we've got to make sure that we're inside of that. You know, we're operating somewhere down in. And again, we can operate anywhere below because most of the time we can put a flow control valve in there and say, okay, I want to limit the flow, so that pulls me way down from the top, so I have a horizontal line coming across there operating at a lower flow up to my maximum pressure. So I can operate anywhere inside of there, but I have to have the valving and the control system to be able to make that happen. So that's what we need to understand. So those are relief valves, and that's a lot of discussion about that, but they're a critical part. They're in some form, they're in every fluid power system, so we need to understand that they're there, and we need to understand what they're going to do. So that's the basic, the fundamental relief valve, or pressure control valve, the valve that controls pressures. Now, there's a lot of other kind of valves, pressure control valves that we can have, and I'll just show a couple of them here just to kind of pique your curiosity. Again, in another course that we teach in fluid power, we would spend some time designing these, looking at what these do, but there's a lot of different things, different kinds of valves that are manufactured. Some of them are very similar. They look and symbol very similar to what we have, but that top one there, the first one, is a pressure reducing valve. And compare it to the relief valve that we looked at earlier, you can see the difference is where the pressure line, this pressure sensing line, is coming from. With a relief valve, the pressure sensing line is coming from upstream. So we're sensing the pressure upstream. When that pressure gets high enough, we open it up and dump it off. But look at this one. This one we have normally open valves. So normally we allow the flow to go through it. So, you know, in a normal situation. But we're sensing the downstream pressure. So let's say that I've got some load downstream here that's very sensitive. I don't want it to break. All right, so what I do is I sense the pressure. When the pressure gets high enough, I'm going to push this valve across, which is going to close the valve. It's going to stop the flow. So that's going to say, hey, when the pressure downstream here gets so high, shut the valve. Don't let the pump keep pushing at us and break us. So we can actually limit the pressure in a certain part of our system, have higher pressure available in other parts of our system. So that's one of the things we can do as a pressure reducing valve. There's unloading valves, which are kind of similar to a relief valve. Again, this is the symbol of a relief valve there. But an unloading valve will basically dump the flow off of a pump in a different way. So it opens up and then allows the pump to not have to push against the high pressure all the time. So it's a little different kind of valve there. There's also sequencing valves, and we'll look at sequencing when we talk about systems, because if we have, for instance, two loads, two hydraulic cylinders, that are connected to our system, and one has a large load on it, one has a small load. Remember, the downstream resistance is what affects the system pressure. So what will happen is, as the pressure comes up, the pressure will get high enough to be able to overcome the lighter load, and so that one cylinder will move and the other cylinder will not, because we don't have enough pressure available to move the second cylinder. So we'll get sequencing in our circuit. Well, we can actually control that with a sequencing valve. So we can sense the pressure and say, hey, I want to make sure that this one load always goes, no matter whether it's a high pressure load or a low pressure load. I want it to go first before the second one does. So there's a lot of instances where we want to do that. One more I'll show here is a counterbalance valve. And again, it kind of looks like a relief valve, but we use it as a safety. So basically, we will not allow flow to go through this thing. We'll put this relief valve in line with a load. And so you'll see these, for instance, on a forklift. So if I've got a forklift where I lift a heavy load off the ground, now normally we don't want people underneath that load, and we take safety precautions to make sure that doesn't happen, but some people end up in there. So I want to make sure that that load just can't fall. I want to make sure that to bring that down, I have to actually activate that valve. I have to pull a lever and deliberately make that load come down. I don't want it just to fall, and I don't want it to fall even with a broken line. So I can actually provide some safety if I have a line that blows that won't allow the load to fall. So I have to actually activate the valve from a different part of the circuit. I have to pull a lever to make that load come down. So counterbalance valves, a lot of different kinds of pressure control valves that we can do. The limitations are endless. So we can do a lot of different things, a lot of different designs, a lot of types of circuits. Again, you'll do this kind of stuff in the other course. It's going to be beyond the scope of what we're going to be able to cover in a couple weeks of the survey that we're looking at in this particular course. So that is pressure control valves that we're looking at, and those are the key ones. Again, the relief valve is the one that we're always going to deal with, so always keep that one in the back of your mind. So the next thing we'll look at then are some volume control valves.